Okay, so here we're going to take a look at binomial probabilities, which they're asking us to find some probabilities that fit a specific scenario. Right, in general, on a test, what you want to be ready for is to read the problem and know what approach you're going to be taking. And these binomial probability ones, it's going to be phrased in the general context of find the probability of blank successes out of blank tries. Right? And what we're going to do is basically say we're going to let x represent the number of successes and n represent the number of tries. Okay, so let's take a look at this first problem. On a slot machine, the first wheel results in a $sign with probability 0.2 each time. That's important because one of the criteria for these binomial problems is that when you repeat a trial, the probability of what you call a success and what you call a failure remains the same each time. So here we can say, well, let's call a $sign a success. We can say the probability of a success is going to be 0.2 for every trial. Now here's the next sentence that tells me for sure what I'm doing. What is the probability that in 12 spins the $sign results exactly 4 times? You got to think that's saying find the probability of 4 successes out of 12 tries or 12 trials. So it tells me it's binomial. Okay, if I identify it as being binomial, I can use the binomial probability formula, which says the probability of x successes is equal to the combination NCX times little p, the probability of a success on an individual trial, raised to the x because we need to have x of them. If p is the probability of a success, then 1 minus p has to be the probability of the failure, and we would need n minus x failures. Right, so that formula is it's in the book, but it's worth memorizing because we will be using it quite a bit. All right, now I'm going to plug in my specific values here. I'm trying to find the probability of 4 successes. There are 12 trials, so it's going to be 12C4 times my P is, I guess I'm going to use parentheses here, it's a little nicer. Probability of a success on each trial is 0.2. We need 4 of those because x is 4. And 1 minus p would be 1 minus 0.2, which is 0.8. And then n minus x is going to be 12 minus 4, so that's going to be 8 up there. Now you got to determine how you want to punch this up on your calculator. The TI-30X2 and a lot of them will be able to do this all in one row. So you can just put down the answer. Other calculators are a little bit more fussy, or if you just tend to hit buttons wrong, you might want to do it step by step. So if you do this step by step, if we evaluate 12C4, then that should be 495. Then if I take 0.2 and raise it to the 4th power, that should be 0.0016. All right, 0.8 to the 8, it's going to be a lot of digits. Hold on, let me punch this up. 0.167777216. Pretty ugly decimal. Usually on a test, I'll say, round to this many decimal digits or whatever. Here, if we punch this up on the calculator, I'm getting 0.13287, and it keeps going. So let's just suppose the direction said round to the 3 decimal places or whatever. So 0.133 would be my probability of exactly 4 times getting the $sign out of 12 spins. Right, the nice part about the binomial probability formula, it always starts off with this probability of blank successes out of blank tries, and the only thing that changes are the values of n, p, and x. All right, let's see what's next. So a bus route from Buffalo to Syracuse arrives late to Syracuse 30% of the time. For a project, a sample of 20 roots are selected. So A, what is the mean and the standard deviation of variable x if we defined x to be the number of the 20 roots that are late to arrive? Okay, so basically if we let a late arrival be a success, x is the number of successes out of the 20 trials. So it's a binomial variable. All right, in our book we have a couple of formulas. If we have a binomial variable, then the mean of that variable x is just going to be the number of trials n times the probability of a success each time, p. So here, that would be 20 times 0.3, which is 6. So we're going to end up with a mean of our variable of 6. So basically what that means is we expect about 6 of the roots to be late out of the 20, because the average number of late roots, if you keep observing 20 roots over and over and over and over again, in the long run you're going to get an average of 6 of those roots to be late. All right, now the formula for the standard deviation is standard deviation of the variable x is equal to the square root of n times p times 1 minus p. And again, that's also in the book. Here, that would mean 20 times 0.3 times 0.7. And if we punch that up and, give an approximation here, that comes out to approximately 2.05. Right, meaning if you observe these 20 roots at a time, you get a mean value of 6, but a standard deviation of 2. So, reasonably 4 lates or 8 lates, maybe even more than that on occasion. But anyway, that's the mean and the standard deviation of your binomial variable. All right, so let's take that value 6, which is the mean, and let's find the probability that out of these 20 roots you get exactly 6 of them arriving late. So again, that's basically saying the probability of 6 successes out of your 20 trials. So I'm going to jump into the binomial formula here, plugging things in already. So I'm going to plug in 6 for x. So it's going to be 20 C6, right? 20 is the number of trials, 6 is the number of successes, times the probability of a success, which here, probability that it's late is 0.3, raised to the 6, because we're trying to find the probability of 6 of them late. 1 minus p would be 1 minus 0.3, which is 0.7, raised to the n minus x, so that would be 20 minus 6, which is 14. All right, similar thing to before, you can work this out separately. Or here, if I try to punch this up all at once, I got 0.19163, but it keeps going. And again, if we just do the same thing here, let's round off. I'll tell you what to round off to on a test, but here let's just round that off approximately 0.19, or approximately 19%. Basically, if I give you a problem where you just have to use the binomial probability once, I'm going to ask you to do that by hand like we have these first two problems. But if I ask you to do a probability that would require you to do a lot of binomial probabilities, we can use Minitab for that. So C, using Minitab, what is the probability that out of the 20 roots, at least 8 arrive late? So that's basically saying what's the probability of 8 or 9 or 10 up to 20. Well, there's no way that I'm doing each of those separately. If you did this strictly by hand, you'd have to do the binomial probability formula over and over and over again, using 8 as your x, and then 9 as your x, and then 10. So Minitab can make this a lot faster. What we're going to do is find the cumulative probability that x, the number of successes, is less than or equal to 7. And the reason I did that, or that I'm going to do it this way, is this would be the probability of 7 or fewer lates, which is the complement of at least 8, which means probability of 8 or more late. So these two things are complements. So what I'm going to be able to do is say the probability of at least 8, or the probability that x is greater than or equal to 8 is equal to 1 minus the probability of 7 or fewer would mean at most 7, which I can do as a cumulative probability. Alright, so 1 minus, let's see what it's going to be minus by. I'm going to go to Minitab to find the probability that at most 7 arrive late. So in Minitab, what I want to do is I got to go into Calc and then into probability distributions and choose binomial. When you do this, cumulative probability is selected, and cumulative probability means whatever value you type in, it's going to find the probability that your variable is that value or anything less than that. I got to type in 20 for the number of trials, 0.3 for the event probability, and then this input column would mean you have a column of values typed into Minitab that you want the probabilities for all of those separately. Here I'm just going to select input constant and punch 7 in. So now Minitab is going to tell me the probability that there are 7 successes or fewer. It displays the answer up in the session window, and I'm getting 0.772272. So I'm going to put that in. So if I subtract that from 1, I get 0.227728. So there's the probability I'm looking for. So Minitab, it takes a little bit of practice to get comfortable using it, but it can definitely save us some time working on problems like that. As always, see how the homework problems go, and let me know if you get stuck on any of them. Good luck, guys.